Okay, hey, good afternoon. Welcome to our session today, Programming the Real World, where we're going to talk a little bit about programming devices and wiring it up to some user interface and so forth. Safe harbor statement, of course, you can read that.
So my name is Jasper Potts. I'm working on IoT and also a client architect at Oracle. I've worked on JavaFX for many years now and also get to play with gadgets and embedded and all those sort of fun things.
Yeah, and my name is Richard Barrett. I'm also architect on IoT. And today, at Java 1 and at DevOps, we did a keynote demo of a connected car. And in this demo, we had two different UIs. We had this the instrument panel with the gauges behind the steering wheel, and then we had this side touch screen that has maps and music and control of all your temperature and everything else sitting over there. And it was wired up to the pedals, and it was wired up to all sorts of the touch sensors on the steering wheel. There were a lot of different components that together made up this demo.
Yeah, and if you haven't had a chance yet, you should go down to the demo grounds, and it's set up there in the Oracle booth, and you can have a play with it. So, at the bottom of the board is this huge bunch of different sort of embedded boards and hardware that are collecting data and controlling all the devices and displaying the UIs. So this is a system diagram of all the pieces involved. So on the sort of bottom end, we have three K64 embedded boards, which are tiny little boards. I used to think a Raspberry Pi was a small board until we started playing with this sort of thing. So, they have 128K of RAM. And so, 512 megs feels very spacious after that. So they're really tiny boards. They have all the same sort of digital I/O pin, GPIO, I2C, etc. that you get on the Pi. And so we had those connected up to some different sort of temperature sensors, light sensors, LEDs, the fan, motor controllers, all kinds of things like that. And then we had three bigger embedded boards, two IMX6 boards and a U3. One of the IMX6 boards and the U3 were driving our two touch screens. And then the other board was our IoT gateway. So it was talking to our little tiny devices, collecting all their data, controlling those guys, and sending up that data to the cloud. So we needed a way to talk between all these devices. So in a car, you'd have your CAN bus. And that's the standard way in cars. So it wasn't really practical for us for demo purposes to put that together. So we did our own sort of IP networking system to put these all together. So what we wanted to show you today was basically all of the technology that went into building that in a much simpler system. So, we basically took each of the sort of concepts that we showed in that main demo and put together a much smaller demo where we can go through all the code and the technical details and exactly how it all works. And, the bigger demo was just exactly the same, but more of it. So this is the system we have set up for the demo to show you today. So we basically have two boards and connected hardware. So we have the Droid U3 board and a touchscreen, and that's going to be running JavaFX on SE Embedded, and that's going to show us an interactive UI connected to our device. And then we have a second board, which is our Raspberry Pi. It's one of the new Raspberry Pi Model B Pluses, which are really quite nice. And then we have three different sort of hardware interface boards coming off that, all connected via the I2C bus. We have an analog to digital converter, which is reading a little joystick. This is basically exactly the same as we did for the pedals. The two pedals we use on the demo are actually musicians' pedals for keyboards, but they just give us an analog signal. And so we just, I wanted something a bit more portable, a bit lightweight, because those are designed for, to be beaten up by, band members, so they're made out of big lumps of metal. So I didn't really want to carry those in my suitcase, so we have a little joystick to represent the same thing. And then we have an RGB LED that's controlled over the I2C bus and an I2C temperature sensor. In the actual demo, we also had a light sensor and a couple other bits, but it all works in exactly the same way. So once you know the principles, you can apply it on the bigger field. So the Droid U3 board is kind of my favorite little board for running embedded FX at the moment. It's a really tiny little board. You know, if you can quite see, but it's a pretty tiny little board. And it's amazingly powerful for its size. You know, it's smaller than a Raspberry Pi, but it's a quad-core 1.7 gigahertz. And so, you know, it seems like you're getting a lot more processing for double the price of a Pi. And has 2 gigs of RAM and a fast GPU. And then the same company who produced that also produce a 9-inch touchscreen, which we have here. The nice thing about it is we've had a bunch of touchscreens for the Pi, but they usually are very fragile and have little wires that break easily. This is nicely in a case and just has an HDMI and USB connector. So it'll work on your Windows laptop or on one of these embedded devices or something. So it's a great little board for carrying around and showing stuff. And it's a pretty reasonable price. It's actually cheaper than a lot of the sort of separate ones we got for the Pi with lots of breakable wires. So it's a quite nice little setup. So we then have our Raspberry Pi, and it's connected up to with I2C to each of these little devices. So I don't know how many of you saw the talk on Pi4J yesterday. So we're going to be using the Pi4J library, and he talked about all the different ways you can connect up devices to a Pi. My favourite by far is I2C, because it's pretty much plug and play. It's much like USB for embedded. There's 4 wires, so you have your positive voltage, your ground, and then 2 data wires, or data and a clock. And you can connect as many devices you like up in parallel, just one after another, and chain them up. And I think we've had at least up to sort of 10, 12. In theory, you can get up to 250, but I think you might have issues before you get there. But generally, you can connect a pile of these devices up. And then each one has a unique address and is individually addressable. And the programming of them is pretty simple, as we'll go into. So assembled here for the actual device, and afterwards, if people want to come and have a look, they can come and have a play. So I took a board that sits on top of the Pi. It just plugs in nicely on top, which is sort of a prototype board that you can then solder wires onto on all your other boards. And so I took these 4 little boards that took me a couple of hours and put some wires up. And basically, I just have the I2C buses connected up to each of the little boards, and then there's a couple of wires connecting up the analog pins from the two-axis joystick up to the inputs of A0 and A1 at the bottom there for the analog to digital. So it's pretty simple to put together your own board. All kinds of applications you can start doing this. Home automation stuff of controlling all kinds of things. Controlling your sprinkler systems. Another one we want to do actually is in our testing labs, we've got lots of these little devices, and so we want to have one device with lots of relays that can remotely power cycle all the little embedded boards. So we're going to have one board with 32 little relays coming off it, and that will allow us to remotely reboot 32 other boards and devices in a test lab. So they're pretty handy things to be able to build upon.
Okay, so I guess at the heart of the implementation of this stuff, we have obviously the little pieces of hardware, and then on the software side, the most fundamental thing is how we define our data model. And this data model is going to run on both of these boards. It runs on the UI side of the board, on the UI side of the project, which is on the Odroid, and it's also going to run on the Raspberry Pi, where the data is being collected. So the first thing that we're going to do is kind of go through our basic application model. Okay, and we created this class, we called it demo model, and it has some properties that we've defined here. And if any of you have done any JavaFX programming, then you'll be familiar with the concept of these properties. A property is an object that holds a value that you can add listeners to, and that you can wire up to another property so that it gets automatically updated whenever that remote one changes. Okay, so by defining our data model in terms of properties, it's going to give us a very easy and convenient way to wire up gauges and other things that we have in our UI to actual physical devices that are running across the network, across this, a network across the I2C bus to these actual sensors. So simple, in fact, that when you look at the code, it doesn't even look like it Well, it's really simple. So what we're doing is we're creating a position X and a position Y. These are going to be what tracks the position of the analog thumb joystick. We have the temperature, which is related to the temperature sensor on the Raspberry Pi, and then we have a display unit, which is going to tell us whether or not the display is in centigrade or Fahrenheit, and then we'll be able to do appropriate UI based on that. And then there's an LED that we have on the Raspberry Pi board that we're going to be able to control from our UI. So we created this application model, and again, it's running in both places. It's running both on the UI board as well as on the device board. We also created another type of property or observable value in our model, which is the temperature. So we have a temperature sensor, and the temperature sensor is going to be giving us some sort of a value. And we want to take that value then and be able to display it in either centigrade or Fahrenheit, depending on the state of this display unit property. So what we did was we created a display temperature observable value, which is based on a data binding. And this data binding takes two inputs. It takes the temperature and it takes the display unit. And then whenever either the temperature or the display unit changes, this compute value method will be called, and it will go through the process of figuring out what the value for the display temperature is. So it just does some basic math. And then finally, we created a class which is special for this demo, and we called it Model Replicator. And what the Model Replicator is going to do is it's going to add listeners to these different properties, the temperature, the position X, position Y, and LED color properties. It's going to add those listeners to those so that whenever they change, it pushes that change across the network to anybody else who's listening. And likewise, if anybody else somewhere else in the network makes a change, it'll push it to the Model Replicator, which will then update these properties. So the Model Replicator is the guy who represents our connection across the network. So this is a little diagram that kind of shows what we're talking about. On the one side, we have our UI gauge, which is going to be showing, in this case, the X position. And so then we have on that board, on the Odroid board, we've got our data model running, and it has a position X property. And meanwhile, over on the Raspberry Pi, we've got the thumb control, and it's going to go through all of its circuitry. And then over on that system, we have our same data model running, a different instance, obviously, because they're on different systems, but it's the same thing, and it's got the position X. So what happens is that when we see when the Model Replicator sees the position X on the Pi change, it will send that information over the network, and then the Model Replicator on the Odroid will see that change, update the position X property, the UI is bound to it, and it all gets updated.
There's all kinds of technologies you could use for doing this replication. In this case, we're using sort of, I just picked something that I knew and liked, which is a library called JGroups. It's been around for, I think, at least a decade. What it does basically is it's sort of a modular stack for building networking. It was built by a guy at Canadian University as a way to teach networking stacks. But it's sort of grown from there. It's used by JBoss for all of their cluster replication. But basically, it creates a peer-to-peer group. So anybody running JBoss with the same name, running JGroups with the same name on the same physical network will become part of the same group. And then you can easily send messages around. And so the nice thing of this is I can run as many clients as I like. So in our car demo, we had 5 different boards, and when we were developing, we had 3 people's laptops, and those can all just connect into that same group and be running different parts of the UI or different parts of the app, and they all just talk to each other.
It's basically like a really simple distributed data grid. It's one shared piece of data that gets pushed to all the different clients, and that they all share.
And so I just wrote some code to basically listen to the properties, send those changes over, and apply the properties apply those changes at the end. But the nice thing is, you could use MQTT or any technology you liked for doing this networking piece of it. But the cool thing is, at both ends, you end up with JavaFX properties. And so, as far as each client thinks, everything is local. They just deal with the properties, they change them, they listen to them, and they think everything's local, and it magically goes across the network. So let's have a look at the code for the I2C piece of it. So there's two libraries out there for I2C. There's the Py4j, which we're using here. It's nicely easy available. It has a pretty elegant, simple API for getting up and running with this. There's also the DIO library as part of OpenJDK. Hopefully, I'll get a chance in the near future to kick the API of the DIO library a bit and make it as nice as Py4j. But for this point, we're showing you the Py4j one at the moment. So the first thing we do is grab the I2C bus. So there's two buses on the Pi. One's on a secondary connector, generally only used for camera control and things like that. You can use it if you really need two buses. We did last year at Java 1, we had the cool robot demo. In that case, we were running off a Pi and we were using both I2C buses because we had a lot of I2C devices. So we had a motor controller that was controlling the actual arm moving around. And then we were using the second bus to have a bunch of accelerometers on each part of the arm, giving us the exact position and feedback for how the arm moved. But so in this case, we've got everything connected up to the main I2C bus, so we just need to pass it in the bus number, which is 1 in this case. So the second thing we're going to do is ask for a I2C device that represents one of those little boards that's connected to the I2C bus. So the first one here is we're getting the temperature sensor. Each board has a unique address. There's a command line tool you can run on the Pi called I2C detect that will list out what devices are available and currently connected to the bus. And you may have address collisions. Most of the devices have a pin, like an address pin, that you can connect up to either plus volts, minus volts, or even some other pins, and that will let you choose what address. So if you want to have two temperature sensors the same connected to the I2C bus, you can do that by changing the address of one of them. So once we've got that, we can open that one up, and then we're doing the same for the analog to digital. I have a class here that wraps the I2C device for the analog to digital converter and has some of the sort of internal knowledge about which registers to read and write and stuff and how. So all of I2C is done in generally unsigned bytes. So you're reading and writing unsigned bytes, but those bytes may represent a floating point number, 12, 14, or 16-bit floating point number. So there's a bit of bit shifting and stuff you have to do, and we'll show an example of that.
In fact, of the entire project, this is the most cumbersome.
Yeah.
So it got encapsulated into its own little class. Other than that, everything was really straightforward. So you just have these I2C devices, and they'll give you some data, and usually the data is in a very simple format.
Yeah. So the last guy is our I2C LED. There's a couple of different ways you can connect RGB LEDs up. You could use GPIO and do it that way. You can use a external pulse width modulation. The challenge is, if you send just a 1 or a 0 to the red part of an LED, it's either going to be on or off, so you can't make any color in between. So for that, you have to use pulse width modulation, which is sending you a wave where you're a part of the time on and part of the time off, and by adjusting those, you can adjust the brightness. But that all gets quite complicated, and the other pain is that if you're varying between 100% on to completely off, it's not linear. That doesn't map to fully bright and fully off. So the nice thing is we're using some little I2C LEDs here, which actually have an Arduino-based chip in the LED. And so it does all of the hard work for making the LED work, and we just send it commands over the I2C bus saying, go to this color. Or you can even say, animate to this color, or create an animation script with a number of different colors. And they have some built-in ones for things like lightning and thunderstorms and other sort of fun things, or sirens, like police, flashing blue sirens and stuff. So, it makes it much easier from us, Generally, I don't want to play with the low-level stuff unless I need to. I'm much more a high-level programmer. I expect like you guys are, and you just want to get on and make the thing work. So that really makes it a lot easier. So the first thing here we're doing is we're sending a command to it to tell it to turn off. This was something I had to put in because I was playing with it at home, and the LED is really bright, and the default mode it turns on is flashing on and off, and it was just sitting there beside me as I was coding, flashing on and off. And after about half an hour of sticking bits of paper and books over the top of it because it was annoying me, I decided it was about time to put the line of code in that actually turned it off when we first got it. So what this is doing is just sending a single byte over the I2C bus. So there's two ways you can talk to the I2C bus. You can either just send and receive bytes like it's an input stream, or you can read and write registers. So just like treat it like a big array, and you can just, so you basically, it's an array of bytes, and you can read and write to different addresses within that. So in this case, so this particular device works in the way of just sending bytes like it's an input stream. So I just send a single byte of O for off, and that's it. So
there's a funny trick that we're doing here. So I told you that the Droid we're running JavaFX on, and that's what's powering this display, which we'll show you in a bit. The funny thing is that we're actually running JavaFX on the headless Raspberry Pi as well. So we're actually reusing some of the basic infrastructure that JavaFX provides to make our coding experience easier, even in this headless environment where we're talking to this device, which is something that, well, I had never thought of before. And there's a couple nice things about that. One is that you get this application model on FX, so it's really easy to do in order to handle starting and stopping and things like that. It also gives you a consistent threading model because you're always called on this event thread, and so you can deal with incoming events and things like that in a nice way. Another one, as you see here, is that we're reusing the JavaFX timeline, which is a animating tool, but we're not using it for animating a UI. We're using it for doing something at a regular basis, and then reacting to it. And the nice thing about it is that it is integrated with the event system in FX, so that you have no threading problems. Normally, if you have some kind of a timer, the timer is going to call you back on some other thread, and you have to deal with making sure that your state is transient or volatile, or you have to use atomic state or some other way of dealing with
or create your own
threads.
sort of event thread and keep jumping onto that, so that every time, because you don't want to be accessing the I2C bus from multiple threads at the same time. You'll get all kinds of weird things happening. So this really makes it a lot easier that you can just not have to think about threading. So that's why I ended up going this way. Is obviously I came from the point of knowing FX, and it's like, well, when I'm writing UI code, I don't have to think about threading. Why should I have to think about threading when I'm writing device code? And also, some of the timeline stuff comes in really nicely. So, for example, on the demo for the car stuff, we were playing around. So when it was off, there's a LED inside of the start button, and I wanted it to sleep like a Mac, so it does the sort of slow fading white and thing. So I could just create a JavaFX timeline that went through a series of values over time and changed a property. And so I've got a JavaFX color property that represents the color of my LED, and I can just animate that color property over time.
Right.
And
so instead of animating a graphical user interface, we're animating a real user interface.
So you can use all your same ways of doing programming pixels as you can programming the physical world. So it turned out to work out really nicely. There's a lot of similarities. So this is where we get into the little bit of low-level stuff that scared Richard earlier. So basically, when you're reading from the I2C bus, as we said, you might want to get a double number. So because these chips are, inside the I2 things are really low-powered, generally really dumb, they do the minimum amount of work possible to get you the data. So they'll give you the data in some really weird esoteric format. And unless people have been around in sort of early computing days, most people haven't delved this deep. I was lucky enough that when I studied computing, I studied it on an electronics course, and so I started with all the sort of low-level stuff and worked up. But most software engineers, this is kind of scary. But basically what happens is we're given 2 bytes, and in this case, those 2 bytes are representing a 12-bit integer number. So we have to do a little bit of bit manipulation to pull the 2 bytes out, take out the bits out of that we care about, and turn that into a JavaFX into a Java int. Once we have that, the reference manual tells us there's this magic number you multiply it by, and that gives you the temperature in Celsius. There's a few nasty steps to go through to get from this weird random 2 bytes it gives me to a sensible value in Celsius of what I want. But the nice thing of all these things is they come with a PDF data sheet, and it's pretty well documented exactly how they work. So it doesn't take long, and once you've done a couple of these, you might end up drawing zeros and ones on a piece of paper and working it out for a little bit, but it's really not too crazy. So once we've read our value, so inside of our timeline, we're happening 5 times a second, we're doing a number of things. And so the first one we're doing is we're reading the value of our temperature sensor and updating our data model temperature property to represent the new temperature. So the second one we want to look at is how do we read the values from the joystick and how do we update the LED color. So reading the joystick is simple because we basically it's exactly the same sort of set of code as we did for the temperature, but we encapsulated it into our analog to digital class. So it's again doing a bunch of reading and cleaning up of the values. So inside my normalized value method, I'm taking it from the value which it's giving me, which is a voltage between 0 and 3.3 volts, and turning that into a nice 0 to 1. And I have a couple of properties I can set on that to set what the lowest value possible and the highest value possible is, because the analog things aren't really that precise. So fully left or fully right isn't necessarily absolutely 0 volts or absolutely 3.3 volts, and the electricity coming out of the plug socket isn't exactly right. So there's little bits of variance in there, and so I'm doing a little bit of cleaning up here to turn it into a nice 0 to 1 value that makes it nice and easy to deal with my code.
Then the LED is a little bit different from the ones that we've been looking at, because these ones have been about reading data. The LED is going to be about writing data, because in our UI we're going to pick the color and then push it onto the board.
So here we're sending a command to the LED, the same as we did earlier. So in this case we're sending more than one character. So we're sending a character to tell it what to do. And in this case, the command C tells it to change to a color. The nice thing is it actually tells it to change to a color over time. So over I think quarter of a second, it will fade to that color. So then we get nice smooth transitions between the color. It doesn't flicker. And then we send it 3 bytes for the RG and for the red, green, and blue channels. And so we're just taking our JavaFX color object, which represents red, green, and blue as 0 to 1. Floats, and multiplying those by 255 to turn them into bytes. And the last 0 and 4 are just telling it what size of the array. So we want to start from the beginning of the array and read all 4 bytes and send all 4 bytes. So it just sends those 4 bytes to the LED, and then it will do our nice little animation to change its color. So next thing we wanted to have a look at was to show you, how did we create the UI. So what I thought I might show you to start with actually is, so we did, I'll show you what we did for the actual car demo, and then we can sort of take that and compare to so if we take our gauge cluster, for example, for the central sort of screen, I have each of my FXMLs for each of the different guys, and so I can open that in Scene Builder. So this is the complete sort of gauge cluster. So the principles I'm showing you for doing stuff in Scene Builder, we did exactly the same thing for the car demo, and it was a really nice experience. So we had a designer who was working with me on it, and he did pretty much all of the Scene Builder work. He created me simple prototypes with sort of dumb bars and colors, and we could start writing all the code, making it all work, and then he could carry on iterating and making it more and more pretty over time while our code stayed the same. And he could move things around and move it 2 pixels that way, and then sleep on it and decide to move it 2 pixels back, and all those things designers do, without really interfering with our development process. So the whole thing worked out really nicely. So let me create a new file. So one of the things he taught me was, the first thing we started this project and we had some ideas we wanted to look like, and I just sort of dove in and started writing code. And I quite like drawing graphics with code. I'm crazy that way. So I was just writing lines and lines of code to draw pretty graphics. And then I got told off and scolded by the designer and saying, well, that's useless. I can't touch that and I can't fix it and make it really pretty. So he said, it's really simple to create a gauge inside Scene Builder, and showed me a trick to do it. So I'll show you the same trick today. So the first thing we're going to do is start with a stack pane. And I can go in and give that my size at 300 by 300. Hope that's reasonable to show here. Yep, cool. So I then want a circle, which is going to represent my... So in this case, I'm going to create a complete sort of 360-degree gauge. And so I want a circle to represent all my tick marks. So this was kind of a handy trick that he showed me as well. So, oops. Where's our radius gone? Oh yeah. So let's make our radius 150. So the way we were doing it for the actual demo was all of the styling was coming from CSS. So we had a separate FXML file and CSS file for all the styling. But just for showing you quickly here, we can do the styling inside in line in the code. So I can give this guy a background color. Oh, actually, he's a circle, so it'll be fill. So let's just get rid of his background color, and then we can add another property for setting his stroke dash array. Now, and then I'll make his stroke width big. So this is kind of a handy trick of using dashes to represent tick marks. So maybe a bit more spacing. So we can quite quickly create, a nice set of tick marks for our gauge. The next thing we need is we want to create our needle for our gauge. So I'm going to pick a region. So we can add our region on top. Now I can't see my region at the moment because he doesn't have any background, so just make him red. So the moment he's the full size. So I want to come down to his sizing, and I want to set his maximum width to be his preferred size, because by default a region will grow as much as it needs to fill the available space. So I don't want it ever to get bigger than my preferred size. I'm going to make it 300 pixels across, so it's all the way across, and we'll make it something like 10 high to be our needle. Now obviously at the moment it goes the whole width across, so we can just go back to our CSS and add a background inserts, and then so top we want nothing, and then from the right we want to come in a bit more than half, so let's say 280. Oop, I can type.
Make it more like 180.
I'll make it 180.
There we go.
Yeah. So that just basically just brings our background in from the edge, so it only represents half. Now, I could have just drawn a line here, but the nice thing of doing a region is that's then infinitely CSS stylable, so the designer can have all kinds of control over it. And you may ask why it goes all the way across. The reason why it goes all the way across is JavaFX has a property for rotation, and the rotation by default works around the center. So the advantage of it going all the way across is now when I rotate it around the center, it moves around my dial. So I have this nice property on that node that I can then just bind up to my value, and as my value changes, it'll move my needle around. So it's a super easy way to draw a dial, and the cool thing is, you can see exactly what it's going to look like inside of Scene Builder and play around with all of the visuals. And the only connection to the code is that binding to the one rotation value. So the designer can do anything they like to make this look cool, as long as he doesn't change that one property that needs rotating. So it works out pretty well. So that's
Okay, so Jasper was talking about how in the car demo we had these FXML files and we have these CSS files. So I want to explain quickly the model that we use for developing UI in this way. So at the root we have our actual demo application, JM demo app, and this extends JavaFX application, right? And it uses the FXML loader to go load our first main screen, which is app.fxml. App.fxml refers to the controller file, and it also refers to the CSS file. So by loading that FXML file, it brings that entire unit, which is a combination of the FXML, a controller, and your theme. That app FXML has inside of it an include. So you can composite a UI based on multiple FXML files. And each one of those units is made up of, again, an FXML, a controller, and a gauge. So what we did was we have our app, and our app is going to have a couple gauges in it. It's got a button in it. It's got a region for drawing the colors and so forth. And so what we wanted to do is to break that out in a modular way. So our designer in Scene Builder can design each one of these pieces individually, and then we can pull it all together into a single app FXML. So here we have our gauge. This is what he looks like, and these are the main components of him. There's a needle, there's a title label, and a gauge label. And the XML is, the XML. But the important things I've put in bold here, you can see that we've got our label that's called gauge label, and it has an FX ID of gauge label. And then we have a region, and it has an FX ID of needle, and we have a label with an FX ID of title label. So gauge label, needle, and title label. Those three names are significant. Because in our controller, which is Java code, what we're going to do is we are going to create three fields that represent those elements. And it has exactly the same names, and they're annotated with FXML. And what happens is during the loading of this FXML document, when it creates its associated controller, it will inject into the controller references to the actual UI elements. So we have our gauge label, title label, and needle accounted for in our controller. Then we've got a couple properties. We've got a value property and a title property. These are the things that we want to allow the rest of our application to modify and manipulate. So that's why they're public. And then we create a timeline because we're going to be doing some animation so that every time the value changes for the needle, we don't just jump to the right place, we're just going to animate to the right place. So then in the initialize method, which is called after this controller has been all injected and ready to go, then you're able to access that gauge label, title label, and needle. So what we do is we create some kind of a timeline or listener that will create a timeline so that whenever the value changes, we'll rotate the needle property. And we're also going to set up a binding to our title label so that the text in that UI element will get updated whenever that title property changes. If we were to look at the application's FXML, it's really quite simple because there's not a whole lot to it other than specifying the style sheet that it wants to use and then having a couple FX includes. But there is something very significant here in this FX include. It specifies the FX ID and it says X gauge and another one called Y gauge. So we had a single gauge FXML file, but we're going to create two different instances of it. We're going to give each instance a different ID. Then in the controller, we are going to create references to those gauge controls. Because remember, each one of those units is made up of the XML document and a controller and a CSS file. Well, in this case, we've got Java code. We would like to be able to refer to the controller of those embedded documents. And so we do this by, again, using the FXML's dependency injection, and we're able to get the controller from those embedded documents available to us. And then what we do is we have our constructor for this controller, and it injects the demo model inside of it. And now, in the initialize method, is where all the real work happens. In the initialize method, it says, that X controller has a value. I'm going to bind it to my demo model's X position. X controller, or the X gauge has a title. I'm going to bind that. I've got Y gauge controller, and I'm going to take its value and bind it to the data model. So we bind all the UI elements up to the data model inside of our controller. And that data model, of course, as we mentioned, is automatically updated whenever the data changes over the network. So that really wires everything together, and we're ready to go. The only thing that we had to do here, actually I'm going to switch to this slide. The only thing that we had to do was at the application level, we just needed to make sure that we start up the FXML loader, and that when we create the application model, we are injecting our data model into it. So it's just a couple lines of code. So, whoops, that's that guy. So that's all the talking. So now we're going to switch and show you the actual demo working in a complete manner. And we are, the last time we did this presentation, it worked really well. So we're going to end some minutes early after we take questions so that you can come up and play with it. Because we're showing this through a little Elmo device, and it doesn't show the performance really quite that well.
It's kind of annoying that you put all this effort and you get a nice optimized performance on the actual device, and then you stick it through a camera that does like 4 frames a second. So it really ruins it. But as I move my little joystick around, the dials should move around, and you see they're flickering like crazy. They're actually really nice and smooth on the actual device. So in this case, I just put up 2 dials to show me my X position and Y position. So if I move it all the way over to one side, we get 100. All the way to the other, it should drop down to 0. And the same for the other guy. But obviously we can connect those up to anything we liked. So on the right here, I was thinking that I have a X, Y position for a color, so I could have connected it up to send the color. So if I touch on the touch screen, move that down.
Let's see
and Rich holds the thing.
for you.
So we get a nice sort of our pink LED, or we can go up to yellow, and I can actually just drag around and it will change. So any of the colors, and it's pretty responsive that as soon as you touch the UI, you get the same color. So that's sort of showing data going the other way. And then we also, at the top we have our little temperature sensor. So somehow it thinks it's 26 degrees. I don't think this temperature sensor is very accurate. It's supposed to be. Maybe somewhere I'm doing my bit shifting wrong, but if I touch it, our temperature goes up. We actually managed to find a helpful helper last time who has really cold fingers, and they made it go down, which is even better. But for me, it's going to go up. And we can switch between our Celsius and Fahrenheit. So our little switch, and then obviously our gauge works exactly the same way. And it's just changing the values which we're displaying. So we can create a little touch switch. But it's just sort of showing what you can do with a little touch UI and connect this up. So you can imagine this being your home control on the wall, and it's controlling your lighting and your heating system and your sprinklers and security and all the stuff for your house. That's definitely my hope, to get that all working for home. And I actually want to have a nice 3D model on my house that I can pan around and zoom in, pinch zoom in on a room and click on the lights and stuff, and I think it'll be really cool. Probably entirely painful to use, but it would be really cool to show people when they come over.
Everybody would think you were very advanced and modern. Yeah, the basic principles behind this really are very simple. If we were going to summarize it up, in this local network, we're just using a very simple library for sharing the data across the devices. We have properties on both sides, and all we have to do is literally for any one particular property, there's a single binding between the UI and the data model. And then on the other end, we just have listeners to the data model that then can push things down onto the actual devices for like setting the LED and so forth.
And you could easily use a remote networking technology via a server, and this could be a phone, this could be your Android tablet or phone or whatever else, or your iPad, and running FX, and then you could run exactly the same app connecting to the same device running in your home. So
that's right. The rest of the application doesn't have to change at all. It just sets the property from a different mechanism.
Yeah.
Can we go back to the slides? Okay, take me back up to the big overview guy. Yeah, 5. Yep. So going back to kind of where we started, in the demo, we had the physical devices, we have the gateways, the bigger devices, and then we have this IoT gateway, then we have the cloud, and then we've got the servers that run on the back end. So the title of our talk was Programming the Real World. And I think we've demonstrated some ways in which you can do that on sort of the local network. What's interesting is to think about this in the broader IoT scope. How does this fit into, the bigger picture? So in the car demo, we had all this local network stuff going on inside the car. Right, and so you could go to the touch screen and you could change the temperature or the fan control, and then we would change the fan blade to speed up how fast it was going, all that kind of stuff. But the other thing that we were doing was we were gathering this data, and then we needed to send it somewhere. So in your typical IoT reference architecture, you always have a thing that acts as sometimes called a router, sometimes called a concentrator, but usually called a gateway. And it's not your typical internet gateway because it lives on the other side of that cloud, right? It's on the device end of the cloud as opposed to the server end of the cloud. But it performs the same kind of purpose. It's going to gather data from multiple devices, many of which might not have an internet connection of their own. It's going to analyze that data. It might filter that data. It might do some local intelligence. And then it could take some of that data and send it off to the server. And we use just normal HTTPS for this. We also looked at WebSockets. There's a lot of different technologies that are out there for doing that, but basically it comes down to normal HTTPS request response or WebSockets. And then on the other end of it, you're going to have some kind of a server. And there's one other interesting principle at work here, which is that most of the time, these IoT gateways are running behind some kind of a firewall, right? Maybe you've got it at home. Let's say that we had this set up at home at Jasper's house. You know, our little Raspberry Pi gateway here is going to be running behind his home network. So how do you control it over the network? How do you do that when you can't actually route anything to this device? Well, usually the way that this is done is that on the server side, you will set up some sort of maybe a message broker. It could be a MQTT or JMS, or it could be some other sort of REST-based system. And then what will happen is that the IoT gateway will connect either periodically or through some kind of persistent connection like a WebSocket. So that actually what you do if you wanted to control the gauges, for example, from your iPhone, is that your phone would talk to a REST API that's running on this IoT cloud server, which then will get that message sent back down to the IoT gateway, which will then disseminate it to the devices to do the things that it's supposed to do. So it's a very, when we're looking at programming the real world for real life, we're going to have some kind of server element running that allows you to be able to route back down to your devices. There's also a couple cool startups out there that are doing things along these lines. There's one called If This Then That. There's another one called Dweet.io. There's some cool things that are out there that you can play with that help you to be able to navigate that portion of it. And then, of course, once data shows up on the back end, you need to be able to analyze it, run it through some big data systems and things like that. In the real world, that's what you would be doing. And so those server elements are an essential characteristic of the entire IoT solution. But when it comes to actually how do you program these things on the small, it's really fairly straightforward, and Java is a really good natural fit for a lot of these sorts of environments.
Well, it looks like we have just over 10 minutes left, so probably the easiest thing is, if you have questions, come up and ask us direct, and then people can come up and play with it, because it's much more exciting to see it for real, and this is such a big room, it's hard to...
Yeah, you can't really see the LED very well from up there, I'm thinking. But so if you have any questions, come on down. We'll be here for a few minutes so that you can see it, play with it, and answer any questions you have.
And thank you everybody for coming.